All right, next up we have something known as Le Chatelier's principle. So Le Chatelier's principle has to do with the situation where you have a system at equilibrium and then you apply some sort of change to that system. And the system responds in a certain way. So here's what it states. If you do something to disturb a system at equilibrium, the system responds in a way that, key word here, partially counteracts what you have just done. So you apply some change to the system always responds in the opposite way of that change. And it will act to counteract the process or sorry, counteract the stress, but cannot do so completely, but rather partially counteracts that change. There are technically two possible causes of the disturbances. These are also known as stresses. Uh, we're going to look at actually three though. There's three things that can be done to an equilibrium system to cause it to change. One is a change in the concentration of a reactant or product. So if you change the amount of something, technically the concentration, then it's going to have an effect on the system. Another stress is changing the temperature. And then the third one, which is technically the same as the first one, but we're going to look at it a little bit differently, is a change in the size of the container or volume, and this is for gases only. So this, number three, is actually, we're going to look at it as a pressure stress. So if you change the volume of a container that has gases in it, the pressure inside will change. So let's take a look at a hypothetical situation. So here's our system. We have A and B that react to produce C and D. And so let's take a look at this situation. We have this at equilibrium. All four substances are present. A, B, C, and D are present in the container. What would happen if more A was put into the system? And so what I want to look at is the initial changes. So initially, what's going to happen? And then I think I mentioned it the other day, or at least to some of you, that at some points, equilibrium will be reestablished. And so we want to look at first what happens and then what happens once equilibrium is reestablished. So we're going to look at this from two different viewpoints. First one being kinetics, reaction rates viewpoint. And then we'll look in terms of Le Chatelier's principle. So first question, if you add more A, first of all, A is a gas, so adding more A to the container will increase its concentration. So keep in mind that it's not about changing amounts per se, but rather concentrations. Very, very, very important. Remember, concentrations of solids and liquids are constant. And so adding more of a solid or more of a liquid is not going to have an effect on the equilibrium system. So since A is a gas, adding more A will increase its concentration. First question, if you increase the concentration of A, what effect does that have on the rate of the forward reaction? Remember, forward reaction is read from left to right. Go ahead and answer that to yourself now. All right, if you increase the concentration of A, that will cause the forward reaction to speed up. The rate will increase. Second question, if you increase the concentration of A, what effect will it have on the rate of the reverse reaction? Go ahead and answer that now. Well, A is not involved in the reverse reaction. A is a product of the reverse reaction. So increasing the concentration of A will increase the rate of the forward reaction, but will have no effect on the rate of the reverse reaction. So what we end up with is something like this. In fact, I wish I could redraw these arrows. Here, I'm just going to draw them above. So remember, when the arrows are equal lengths, that means equal rates. So if we add more A, that's going to speed up the forward reaction while not affecting the rates of the reverse reaction. So at some point, though, that now faster forward reaction, it's going to slow down, the reverse reaction is going to speed up, and a new equilibrium will be established. Notice that both those arrows are the same length, but they're different lengths than these arrows here, indicating a new equilibrium. All right, so when the forward reaction is faster than the reverse reaction, because of the change, we say that the equilibrium or system shifts to the right. So now again, shifts to the right means this: the forward is faster than the reverse, and there's implications on the amounts of the substances because of this. So let's talk now in terms of Le Chatelier's principle. If you add more A to the container, the system is going to respond in a way that gets rid of the A. Remember, we have equal rates, we have balance here. And so if you disturb the system, it's going to try to reestablish equilibrium. And so the only way it can reestablish equilibrium here is getting rid of not all of the extra A that was added. Remember, it can't completely counteract the stress, but partially counteract the stress, meaning that some of that extra A is going to be used up. It's going to be used up in the now faster forward reaction. So again, looking back here, we see, actually I should have written A plus B here. A plus B makes C plus D. A plus B, I know there's coefficients there, but we're just going to focus on the substances. So if we look here, we see that A is reacting faster than it's being produced. It's being consumed faster in the faster forward reaction than is being produced in the slower reverse reaction. And so again, that has implications on the amounts of the substances in the reaction. So again, point being, if the stress makes it so that the forward reaction is faster than the reverse reaction, we call that a shift to the right. All right, so again, equilibrium at some point will be reestablished. And when it is reestablished, what will happen to the amounts of the reactants and products? How do the amounts of the reactants and products compare to when before A was added? So here's how it works. Forward reaction is faster than reverse reaction initially. At some point, equilibrium is reestablished. What effect does this have on the amounts of A, B, C, and D once equilibrium is reestablished? Well, A is involved now in the faster forward reaction, but because the system can only partially counteract the stress, the amounts of A will be higher than what it was initially. Well, again, the system is trying to get rid of A. How does it get rid of A? It gets rid of A by reacting it faster. Well, what does A react with? It reacts with B. So B is going to be consumed faster than it's produced. So the amount of B is going to decrease. How do you get rid of A? You make it react faster. When A reacts faster with B, you make more C and more D. So when the equilibrium shifts to the right because of the addition of the A, the amount of A will increase, again, because that's what caused the equilibrium to shift in the first place. The amount of B will decrease. It's being consumed at a higher rate now than it was before, and so it's going to be used up faster than it is produced. And then the amounts of C and D will also increase. How about changes in concentration? So when you add A to the container, equilibrium shifts to the right. What effect will that have on the concentrations of each of the substances once equilibrium is reestablished? Well, since the amount of A went up, its concentration will also increase. And because the amount of B went down, its concentration will also go down. Concentration of C, well, its amount went up, so its concentration goes up. And concentration of D, its amount went up, but its concentration is not affected. Why? Well, if we look back in the original equation, D is a solid. So though the amount of D increases, its concentration does not change. Next question is, what effect will adding more A have on the value of the equilibrium constant? So taking a look at our equilibrium expression, we have concentration of C squared over concentration of A times concentration of B. Now, if I recall, K's value depends only on one thing, and that one thing is temperature. And so since the temperature is not changing, K's value will not change. Well, why not? Though the amounts and concentrations of A, B, and C are all changing, the ratio, believe it or not, does not change. It will change, though, if the temperature changes. All right, let's try another, and then I'm going to do some generalizations. All right, question is, what would happen if if some B was removed from the system? So again, we want to look at initially what happens to our system, and then once equilibrium is reestablished. So let's go ahead and write those. All right, first question. If you remove B, first of all, B is a gas, so its concentration will decrease. What effect does removing B have on the rate of the forward reaction? Go ahead and answer that. Well, if you decrease the concentration of B, since it's a reactant in the forward reaction, the rate of the forward reaction will decrease. And if you decrease the concentration of B, what effect does that have on the rate of the reverse reaction? Well, B is not involved in the reverse reaction. It's a product of the reverse reaction, so the reverse reaction does not change. Again, at some point, equilibrium will be reestablished, different than what we started with. So notice I have these shorter arrows here, and we have a new equilibrium. So what do you notice about the forward and reverse reactions? Well, it looks like the reverse reaction is faster than the forward reaction. When that is true, we say that the equilibrium shifts to the left. Let's think in terms of Le Chatelier's principle. If you remove B from the container, what does the system want to do about that? Again, the system always responds opposite of what the change is. So if you add A, like in the last example, the system's going to respond in a way that gets rid of some of that extra A that was added. If you remove B, if you take some B out of the container, the system's going to respond in a way to replace all, not all, some of the B that was removed. It can do so by speeding up that reverse reaction, at least relative to the forward reaction. So what happens to the amounts of each of the substances? How do they compare once equilibrium is reestablished to what it was before the stress? So notice that A is being produced faster in the faster reverse reaction than is being used up in the forward reaction. So the amount of A increases. Well, B is also being produced faster than it's being used up, but what caused that in the first place? What caused that is removing some B from the container, and the system can only partially counteract the stress, so ultimately the amount of B will decrease. Once again, how do you make more B? Well, you make more B by reacting C and D faster. And so the amounts of both C and D are going to decrease. How about changes in concentration of each of those substances? Since the amount of A increases, its concentration will increase. Since the amount of B decreases, its concentration will decrease. Since the amount of C decreases, its concentration will decrease. And since the amount of D decreases, its concentration still is unaffected. So it's still a solid. How about equilibrium constant? What happens to that? Well, temperature is not changing, so K does not change. All right, so let's make some generalizations. And I don't really want you to just memorize these generalizations and memorize these trends. Understand Le Chatelier's principle and then use this to help support your thinking. Here's how it works. Let's go back to our first example. If you add a substance, which way does the equilibrium shift relative to that substance? Well, if you add A, which way does the equilibrium shift? The equilibrium will shift to the right to get rid of some of the A. So when you add a substance, the equilibrium will shift away from that substance. In this case, to the right. If the equilibrium shifts away from a substance, what happens to the amount of that substance? Well, the amount of that substance will decrease unless what caused that shift was adding some substance. Like we did A, that's why the amount of A still increases. If the equilibrium shifts towards a substance, what happens to the amount of that substance? Well, equilibrium shifts to the right towards C and D, and we see that the amounts of C and D both increase. If you remove a substance, which way does the equilibrium shift relative to that substance? Well, we saw here when you remove B, the equilibrium shifts to the left. So removing a substance, the equilibrium will shift towards that substance. And if the equilibrium shifts towards a substance, what happens to the amount? The amount will increase, like A, unless what caused that shift was removing some, like in B, so ultimately its amount decreased. And for C and D, since the equilibrium shifts away from C and D, the amounts of both C and D decrease. So again, you understand from both a kinetics viewpoint and Le Chatelier's principle which direction the equilibrium shifts, and then what effect that shift has on the amounts of each of the substances involved in the reaction. All right, let's take a look at another stress. This time we're going to look at temperature stresses. Notice this time we have a thermochemical equation. We have the heat term on the right side. How would you describe this reaction then? Since the heat term's on the right side, this reaction is exothermic. Now, technically, the forward reaction is exothermic and the reverse reaction is endothermic. But since it's on the right, we'll say exothermic. Easier to explain it that way. So, first one, what would happen if you increase the temperature? Well, let's do this. When we do temperature stresses, think of energy as a substance. Now, how do you increase the temperature of an object? Do you add energy to it or do you remove energy? Well, of course, you add energy. So when we increase temperature, think of it as adding energy. Okay, that's one way to think of it. So let's go with kinetics though. So again, let's label initially what happens when you increase temperature, and then once equilibrium is reestablished. If you increase the temperature, what effect does that have on the rate of the forward reaction? The rate of the forward reaction will increase. And if you increase the temperature, what effect will it have on the rate of the reverse reaction? Well, the rate of the reverse reaction would also increase. Remember, if you increase temperature, particles are moving faster and they're involved in more collisions. So what happens is we end up with this. Both rates increase, but the endothermic reaction increases more. The endothermic reaction, in this case, the reverse reaction, is more dependent on temperature than the forward reaction or the exothermic reaction. So we get that. And again, at some point, equilibrium will be reestablished. So I should write substances here. Sorry, I keep forgetting to do that. A new equilibrium will be established, different than our original equilibrium. Let's think in terms of Le Chatelier's principle. If you increase the temperature of the system, what does the system want to do about that? Again, the system is always going to respond opposite of the stress or change. So if you increase temperature, the system's going to do something to decrease the temperature. Now, how do you decrease the temperature? Which reaction must be favored in order to decrease temperature: the endothermic reaction or the exothermic reaction. Well, if you want temperature to go down, you need to favor the endothermic reaction, in this case, the reverse reaction. So reverse reaction speeds up, uses more energy is absorbed. Ultimately, the temperature will go down, not completely back to what it was before, but closer to what it was before. So either way, we see that the forward reaction is slower than the reverse reaction. We call this then, of course, a shift to the left. Now, if the equilibrium shifts to the left, what happens to the amounts of A, B, C, and D once equilibrium is reestablished? Well, the amount of A is going to increase, right? You're going to speed up the endothermic reaction, in this case, the reverse reaction, to make more A and more B. And if you're speeding up the reverse reaction, that means more C and D are going to be used up. So the amounts of C and D both decrease. How about changes in concentration? Well, since the concentration of A increased, the amount of A increased, its concentration will also increase. Same thing with B. You can't make more A without making more B. So both of their amounts and concentrations increase. Concentration of C decreases and concentration of D is not affected. How about K? I think this time it's going to change because K's value depends on temperature. Let's again look at our equilibrium expression. If you increase the temperature, what happens to the concentration of C? It goes down. And if you increase the temperature, what happens to the concentrations of A and B? They both go up. So we see that the top is getting smaller and the bottom is getting bigger. So what effect does that have on K? K will decrease. So how about this? If changing the temperature causes the equilibrium to shift to the left, making more reactants, using up more products, having less products, then K will decrease. If changing the temperature causes the equilibrium to shift to the right, making more products, having less reactants, then K's value will increase. Let's do one more. What would happen if the temperature is decreased? So if you decrease the temperature, what effect does that have on the rate of the forward reaction? Well, the rate of the forward reaction would decrease. And if you decrease the temperature, what effect would that have on the rate of the reverse reaction? Well, decreasing the temperature is going to slow down both of the reactions, but it's going to slow down one of them more. So in this case, we see something like this. Eventually, equilibrium will be reestablished, different than what we had originally. So we see that the forward reaction is faster than the reverse. When the forward reaction is faster than the reverse, we call this a shift to the right. So again, if we think about it, if we go back to our thermochemical equation, to decrease temperature, we do so by removing energy. And if we remove energy, which reaction is favored? If the temperature is lowered, which reaction is favored? Endothermic or exothermic? The exothermic reaction is favored. Equilibrium shifts to the right. So if the equilibrium shifts to the right, what effect does that have on the amounts of A and B? They both decrease. The amounts of C and D both increase. Can't make more C without making more D. Changes in concentration, A and B go down, C goes up, D is not affected since it's still a solid. Effect on the equilibrium constant. Well, again, if we look at our equilibrium expression, concentration of C increases, where the concentrations of both A and B decrease. So K will increase. All right, there's one more stress, pressure stresses. We'll talk about that one next time. All right, thanks for watching.